Hello and welcome back to the lProlog and HOLP tutorial. In this video we'll be extending our knowledge of the typed aspect of lProlog by introducing custom and polymorphic types. To illustrate polymorphism, let's go back to some of the predicates we saw in the last video. We had a predicate called member and a predicate called length. And the types of those predicates were specifically concerning lists of strings. But if you think about it, apart from test inequality, you don't really do anything specific to strings. The elements of the list you're getting the length of, for example, could as well be integers since you're only counting the number of elements. It would be neat if we had a way to say that at the level of type, and indeed there is one. Simply replace the type string with a logic variable. So let's go ahead and change that with a. So notice again capital letter because it's a variable, and let's change that to a, and we'll leave the int here since we need an integer to return the length. So let's save this, and without changing our predicates, let's hide this and let's compile polim, let's link polim, let's ggsim polim, and then let's test it on, for example, member x of a list 1, 2, 3, and the substitution is 1, 2, and 3. And let's test length 2 of a list 1 and 2 and 3, and it will give us len equals 3. Now we've seen some types in the previous videos. We've seen that 1, 2, -1, -2 are integers, so of type int. We've seen that hello and goodbye, in addition of being my least favorite Beatles song, are strings. And then we saw lists. Now what we would like to do also is create our own types. Just having integers and strings is simply not enough. Luckily, we can do just that, and to illustrate that, I'm going to define, in a vile attempt at winning the hearts of ML programmers, a type that they will recognize, adopt, and cover with their love and affection. And yes, this is demagoguery.
Demagoguery, you mean? By demagoguery, I mean demagoguery. I thought so.
And the type I was talking about is the option type, or the maybe type, as Haskell programmers might know it. For those who don't know it, this is a type of data that can either be some relevant information or no information at all. It can be nothing or something. We'll see an example of use in a moment, but right now let's see how we will define this type. Say, for starters, we want an option type that holds either the value none or the value of some string. And let's call it option string. We'll go to the signature file, and we'll define those types exactly as we did before. So type none is of type option string, or let's write an option string, and the constructor sum, which will hold a string and give you an option string. Let's save this. Now if I try to compile this, I'll get an error. That's because right now option string is not known. It's just a token, a symbol. The compiler doesn't know what it is. Is it a predicate? Is it a constant? Is it a bird? Is it a plane? The compiler has to know. And the way to tell it is, as with anything else, you declare it. So you want to say something like, I'm declaring a symbol called option string, and I want it to be a type. So we're kind of attempted to write type option string, that is a type, but this is not possible. So some of you know why, some of you don't, and I'm not really going to dwell on it because I'll have to talk about type theory, and this is not really the place for it. All I will say is, for consistency reasons, you have to have some sort of hierarchy, some separation. So when you're declaring symbols that will be predicates or constructors, you use the keyword type, but when you're declaring something that will be a type itself, you use the keyword kind. If you want to know more about it, look up type theory or read the book I pointed to on the first video. Although if you are not familiar with type theory, it will be tough to understand, and I feel the need to remind you that type theory is absolutely not a required background to follow this tutorial. Now let's move this. So as a convention, we always declare the kinds before the types, but you can do in the other order if you want. Now let's save this. And how about if we wanted to have option types for integers or lists? Should we create separate option types for every one of them and separate non and some constructors for every one of them? Since we already know polymorphism, how about just generalizing the options? So we can change this, for example, the sum, to something that takes A and give you back a type option of that type. So let's change this to A, and instead of having option string here, we'll call it simply option, but now the kind is different because option by itself is not really a type. You have to supply it with a type to be a type, to get a type. So the kind of this will be type arrow type because it has one parameter. So if you give it string, it will be option string. If you give it an int, it will be option int, etc. We'll see an example of use in a moment, but I want to declare another type now. How about another type that is common to the functional programming community, the pair type? Pairs are just couple of objects. The constructor of pair, let's write it down, let's call it pr, and it will take an element of a certain type, another element of another type, and it will give you a type that we'll call pair of those two types. And as with option, we have to declare this thing because it's not known for the moment. And we'll declare it exactly in the same way, pair, but this time notice that option had only one parameter where pair has two. So pair will be type arrow type arrow type. Let's save this. Now I gave two different types here, but of course you can have a pair of ints, but you can have also a pair of an integer and a string, or a string and an integer, or a list and an int, or anything you want. Now let's see a practical use of these types. Say you have a list of locations or places in Age of Empires map. These locations have two pieces of information. The first one are coordinates, and to simplify, let's say that they are just integers, and the other information is eventual resource on that terrain. So now that you're comfortable with declarations, I'm going to go quick. I'm going to declare a type loc, that is a constructor for locations. It's going to take a pair of integers. That would be the coordinate. It's going to take an optional resource, and this will create a location. So see here, it doesn't end with an O because this is not, loc is not a predicate. So here we have two new things, resource and location, that we'll have to declare as well, and these are types, so we'll introduce them with the keyword kind, resource, and location are type. Now another thing we're gonna have to do is introduce some resources. So let's say food, gold, stone, and what was the other, wood, are resources. And now let's declare the type of our predicate that we'll call filter locations. That will take a list of locations, and after filtering it, we'll give back, again I'm using the input-output terminology, location, but this will be a predicate, so it ends with type O. Now let's save this and let's go ahead and code it. Filter locations of an empty list will be an empty list, and filter locations of a list that starts with a location that has certain coordinates that we don't care about, and none. And then tail will give you back a filtered list or filtered location. Let's keep it with filtered list if the predicate filter locations called with that tail will give you that exact same list. So what we did here is keep this element out of the next call to the predicate. Now, what happens if the first element or the head element is a location with the resources on them? Let's write it down, log p, this time with some resources, and the tail. This will give you also a filtered list. If so, filter, let's just copy this. So this will give you a filtered list, but this time, instead of keeping this out, you're going to add it to the filtered list. You want to keep it in the result list. So we're going to construct a list with that filtered list in the tail position and the head element of the previous list. So let's keep this in here. Let's save that. So here is a nice place to introduce a little thing that you can also do in lProlog. If you have two clauses or two rules like we have here that have exactly the same body, the body is what's after the turnstile. The turnstile is this, the colon hyphen. If you have two clauses that have the same body, what you can do is just link the two heads with an ampersand, and this will tell you this thing implies both this and this, which is kind of what we're looking for. Now let's have that saved, and let's go here and tgcc, tglink, and tgsim, and let's go ahead and test our newly written predicates. And now, to gain time, I'm going to snap my fingers like in the Harry Potter and the Methods of Rationality book that I recommend, and the list of locations will magically appear. Ta-da! Okay, so we're saying filter all this list. So as you can see, location on coordinates 1 and 2 has nothing, 3 and 6 has some food, all those have some gold, etc. And give me the filtered list. We call it with that, and it says the answer substitution is the location 3-6 with some food, some gold, and some stone, and none of the locations with nothing on them, which is exactly what we wanted. So we want no more answer substitutions. And now I'm going to give you a final little trick. Since you're no longer beginners, I lied when I said that lists must have the same type, or rather it was a yes or no, yes and no lie. You can have different types in a list, and let me show you how. Say you want to have a list that can hold things of type integers and strings. All you have to do is declare a type, call it different type, which has type, and then declare a type of injection of integers that will take an int to that type that we just created, and a type of injection of strings that will take a string to the type that we just created. And now you can have a list of diff t and use it any way you want. So yes, the list has the same type or has one type, but the elements of that type can hold different types or element of different types. And as an exercise, you can go ahead and write a number int predicate, for example, that will have as first parameter this, a list of different t, and as a second parameter, the number of integers in that list. So it will do exactly the same thing as this predicate, but instead of just going through the head and not caring about it, it will only count the heads that are an injection int of something. But what we'll do right now, let's erase this. What we'll do right now is mess things even more, because again, since we know polymorphism, we can change all these things to just an injection of a certain type A into diff t and have only this. So let's save this, and with that you can do a neat trick. So I must confess I've never used this in my day-to-day life. Let's compile. No, we saved everything. Okay, link and sim. So I've never used this, but who knows, maybe one day I will, and maybe one day you will. So let's show you this. Now, without changing the membership predicate that we have here, we're gonna call it a little differently. So first of all, let's call it with member X of a list that contains in1 and in A and in2, and it will tell you the answer substitution is either in 1 or in A or in 2, which is normal. Now let's call it a little bit differently. Let's call it member in of a certain X inside the same list. So let's just do, we can do this, yes. Let's call it with member in X, and this will tell you the same thing. So X is 1 instead of having in, right? X is 1 or A or 2. Now what you can do is actually condition the X that you'll have to a certain type. So you can tell it in X that would be of type int, or I'm looking for an X of type int in this list, and this time it will tell you 1 and it will tell you 2, and it won't tell you the A. You can do the same thing by replacing the int with a string, and this time the X is only going to be the A, not the 1 and 2. So if you found it a cool use for this, let me know. I would love to know your predicate. And if you don't, just keep it in the back of your head in case you need it one day. Right, this ends our video. My name is Z.A.C.K, and this was the 5th video of the tutorial of HOLP and lambda prolog. Thank you for watching.